Without further ado, please welcome with a warm round of applause, Professor Walter Lewin.
A measurement without knowledge of its uncertainty is not very meaningful. This is so key in experimental physics, and yet it is not covered in high school physics, and it is not covered in any college physics books. But it is so important that I want to repeat this statement. A measurement without knowledge of its uncertainty is meaningless.
It's well known that gravity pulls two objects together with a force proportional to the mass of one times the mass of the other, divided by the square of the distance between them. This equation is called Newton's law of universal gravitation. It's taught to school children the world over, and it predicts the motions of the planets and moons and asteroids in our solar system with incredible precision. However, Newton's law of universal gravitation isn't actually a universal law. First, we know that when the gravitational force in question is really strong, Newton's law is just wrong. And second, we know that when the gravitational force in question is really weak, we don't know whether it's right or wrong because gravity gets too weak to measure. Only in between, like on the scale of the solar system, do we know that the law of gravitation reasonably applies.
If you compare 801 with 802, thereby comparing electricity with gravity, you will see that electric forces are way more powerful than gravitational forces. And the way I can best show you that is by taking two protons, which are a distance d apart. Here is a proton, and here is a proton, and they are separated by a distance d. They repel each other. And the force by which they repel each other is, of course, extremely easy to calculate. We know Coulomb's law. That law is called after Coulomb. And so the force, the electric force with which they repel each other, this is just the magnitude now of the force, is the charge of the proton, which is 1.6 times 10 to the minus 19, but I have to square that. I have to multiply it by Coulomb's constant, which is 9 times 10 to the 9th, and I divide it by d squared. That's the electric force. If I want to know the gravitational force, which is the force with which they attract each other, these are repelling forces, but I just want the magnitudes here, then I have to take the mass of the proton, which is 1.7 times 10 to the minus 27. I have to square that. Remember, m1 times m2 times the gravitational constant. The gravitational constant in SI units is 6.7 times 10 to the minus 11, and I divide that by d squared. If now I compare the electric force with the gravitational force, so I divide one by the other, notice that the d cancels. They both have d squared downstairs. And so you will easily be able to show that this ratio is roughly 10 to the 36. So the electric force is 36 orders of magnitude more potent than the gravitational attraction. This teaches you some respect, perhaps, for 802. If these were the only forces that acted on the protons, and you bring them in the nucleus, which has a size of only 10 to the minus 12 centimeters, then the acceleration that the proton will experience is the electric force divided by the mass of the proton, F equals ma, basis of 801. And if you take this electric force, when you make d 10 to the minus 12 centimeters, which is 10 to the minus 14 meters, and you calculate this ratio, you will find that it is 26 orders of magnitude higher than the gravitational acceleration on Earth. 26 orders of magnitude higher. So you wonder what the hell holds the nucleus together? If there is such a tremendous force on these protons. Well, what is holding them together are the nuclear forces, which we do not fully understand, but thank goodness the nuclear forces are not part of 802, so I'll leave that alone for now. So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together. And now you may say, that's very inconsistent with what you just told us, because didn't you tell us that D cancels if you compare gravity with electricity?
Yes, but keep in mind that most objects in the universe have only a very small amount of charge per unit mass. The Earth and Mars have each a charge of about 400,000 coulombs. The gravitational force between them is therefore about 17 orders of magnitude larger than the electric force.
So even though our immediate surroundings are dominated by electric forces, including your own body for that matter, the behavior of the universe on a large scale is dictated by gravity.
And second, we know that when the gravitational force in question is really weak, we don't know whether it's right or wrong because gravity gets too weak to measure.
On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together.
A measurement without knowledge of its uncertainty is not very meaningful. But it is so important that I want to repeat this statement. A measurement without knowledge of its uncertainty is meaningless.